Okay, so all right. So did you guys have any questions about this uncertainty in the x-intercept here? No questions on any of this so far? Okay, fantastic. Honestly, I think that's pretty straightforward, right? It's a little bit on the long side, but just make sure you're careful on entering your calculations. You should be able to get through that pretty easy. And it's actually pretty much what you'd think it is, right? Notice the same square root square phenomenon going on here. All right. So an internal standard, this is going to be the known amount of a compound. This is different from an analyte. This is added to an unknown, and you will know what your internal standard you're putting in is. Okay? So you'll be able to know what the concentration of internal standard is. It's not the same. It's not necessarily the same compound as the analyte. Okay? And so the signal from the analyte will be compared with the signal from the internal standard to find out how much analyte is present. Internal standards are incredibly useful for a number of reasons. This is one of the big ones, though, especially when the quantity of the sample analyzed is not reproducible. So if you have a method where you can't reproduce the intensity, or maybe even the position, like the peak positions, having an internal standard can standardize all those measurements so you know how far off you are in each measurement. Does that make sense? And then you can use that to correct all the measurements. You guys have actually seen an example of this. Can anybody tell me the example? I'll give you a hint. It's in organic chemistry. Starts with an M. So it starts with an N. Next letter is M. Next letter is NMR. Nuclear magnetic resonance. You guys remember TMS? That's your zero signal every time. What is that? Internal standard. Did I just pull a tooth? Maybe several, I don't know. That was rough. Okay. That's obviously an internal standard, right? And notice, it's a different compound than your analyte. You're not measuring matrix effects. This is different than spiking. This is having a standard you can measure and know where its position or intensity, or maybe even both, that you can just measure every time and then correct your spectra to that. This is very useful in a variety of ways. There's many techniques that the intensity of the peaks, like infrared and Raman spectroscopy, the intensity of the peaks change all the time based on your ambient conditions. Like today it's 24 degrees Celsius in the lab. Next day it's 25. Well, there goes all my fucking intensities. They're all different now. Okay? And so what I use then would be an internal standard, right? And then I can correct all my intensities up to that, just, stretch all the spectra that don't have the same, take all the peaks, make all my internal standard peaks the same size, right? And then all my intensities will be corrected. You understand what I'm saying?
So you're just correcting the peaks based on the change.
Yeah, I'm correcting the peak heights, in this case, based off an internal standard. In the case of NMR, I correct the positions based on my internal standard.
So the peaks, the internal standard would be the temperature, like the change of the temperature?
Well, the internal standard would be something that would be 100% the same conformer, and so it would not change considerably with temperature.
But it's like the values that you're changing based off of temperature.
Well, temperature would be one reason those values would change.
Yeah.
And so in infrared or Raman spectroscopy, peak heights change based off the temperature. That's one of the reasons they change. As you lower temperature, they actually get less and less broad, and they get higher and higher. And the reason for that, if you're curious, is because the broadness of peaks in infrared and Raman spectroscopy is actually microwave rotational states. The more temperature you have, the hotter it is, the more kinetic energy you have in your system, randomized kinetic energy, the more rotational states you have. And so you get broadening of the peaks, but they get shorter. No, you can.
What would be the internal standard in that case? Like, if it's a known compound, like, is it like something?
Tetramethyl. Something like tetramethyl would be good. Simple compounds that don't have conformers and have very really nice and distinct peaks that nothing else interferes with. It's best if they only have a very limited number of peaks. Tetramethyl is not a perfect one, but it is one you can use.
Oh, so you use that because you can
find the peaks.
Yeah, you can find it easily in comparison to the.
Yep.
Okay, so you know what's your.
Exactly. And you don't want your peaks to overlap, right? If they're overlapping, then they'll build off each other. Which it's better if they don't, but you can get away with it. Yeah. And that's a bit more of a complex example. If you want to talk about the infrared Raman one, we can talk about it. I do have like almost 30 publications in that. But like the microwave is better one. NMR is a perfect example of internal standard because everything around NMR requires an internal standard. And that's because they can't get magnetic fields are all differences and fluctuate with the electricity. And so they can never get the same strength of a magnetic field. It's almost impossible. And you can't get it, perfectly aligned with the magnetic field. And there's a variety of factors in there, but suffice to say, no two NMRs would be comparable without an internal standard. Does that make sense? Are you seeing how this is an incredibly powerful technique? Okay. It's used a lot for instruments, but it can actually be used in situations where you don't have an instrument per se. Like you're just looking at, you actually use, to a degree, you could use an internal standard on a chromatographic. Remember the chromatography plates? You could use an internal standard there. Yeah. It'd make your life easier. Something that has a 100% movement rate, and then you put a line right where it goes up. Remember the leading end? No, we didn't. No. We, well, kind of. We have the solution, right? And that has our 100% mobility. But yeah, it's not internal standard. We could have put something that would be a die that would move 100% with our solution. That's especially useful if it's something you can't identify easily. Like if you're using like pure acetone, it'll evaporate so fast you can't draw it. But we didn't use pure acetone. So. The response factor, this is the relative response to the analyte and standard. And that's the response factor F. That will compensate for the changes in experimental conditions when the I of X, you guys know what the I of X represents? The intensity of your signal. So typically this would be like peak heights, but in a method like NMR, where it's the degeneracy technique, that could represent the intensity of your signal is actually a position when you plot it in NMR. So this is going to vary for same concentration of X, because that's why we need internal standard, right? Even though we got the same concentration, our peaks are changing. So the internal standard is going to be added. Standard is different from the analyte. It has to be something that is different, and it has to be distinct. So it's not going to look like the analyte. Okay? If you don't do it distinct, you can't find it, right? Typically, this is not as hard as it might sound. You don't need huge separations. It just needs to be a position you know where it's going to show up. Okay?
But how do you know if it's going to be different than your analyzed?
Typically, if it doesn't have the same functional groups. No. Which is one of the reasons I was talking about, like TMS has essentially zero shielding because it has all those strong electronegative groups. So there's very few things you do in organic chemistry that would be similar to TMS, right? If you're doing things that are going to be like TMS, you'd actually need a different internal standard. So, or it would have to be different enough that you can tell the difference. Yeah. If you started doing something that you don't know which one's going to show up before and after, TMS would be a bad choice, right? You could really screw that up. Yeah. And people do. Don't think they don't. They really do. And then this is the formula. And notice it's just a factor formula. This does make an assumption that these factors are going to change based on a essentially linear change. They'll have the same percent change throughout. That is not actually true for many methods. For example, you cannot count on that to correct peaks in a Raman spectrum, in Raman spectroscopy. Not the peak heights you would, but the peak positions you would not. Because it actually has a logarithmic change on the peak positions. It's an energy scale. But like NMR, you could. This works.
So is there a different formula for that?
No, you would have to correct them by region, or you would have to correct the forces rather than correcting the resulting energy, because that would give you a linear change, direct percent change that you apply this to. Anyways, it's a little beyond the scope of this class, but yeah, I figured how. You guys okay with reading this? You're on known, right? Your internal standards here. Okay. And then that's your factor. Typically, you're going to be solving for that first. But it could already have a standard factor. Like, for example, this is inside the program when you're looking at NMR. You don't even know what happens. By the way, have you ever heard of what that's called, where you don't know what it's doing? It's called black box. It means that essentially it's a black, opaque box that you can't see through. You don't understand what's happening. And it's one of the most dangerous things in science. Because when the black box fails, like they always do at some point, the people using it probably usually don't know what the hell that's happening. No idea. Like they can have something that reacts with TMS, they can have something that the signal interferes with TMS, yeah. And then they get these weird NMR results and they have no idea what's happening at all. And typically they'd have to call an expert. This is an example of the formula. I mean, it's not difficult. I think you guys are okay. Notice this is typically like an A for the peak areas. When you're talking about peak intensities, really they typically are represented by areas, okay? Not by the heights. Remember that? We had that same thing in NMR and infrared, right? Peak areas are representative of your intensities, not peak heights. So, for the sake of accuracy, it's best to prepare a series of standard mixtures of analyte plus internal standard and prepare a graph like you'd see in figure 5.10. The response factor is going to be the slope of that graph. And the intercept should be statistical limits of 0. Again, what does statistical limits of 0 mean? So your y-intercept should be something very close to 0, right? Within your statistical limits, you know, your confidence interval of 0. Does that make more sense? It'll never be 0 in real data, right? It's not how real data works. There's always error, right? An interesting side note is the big difference between organic chemistry and analytical chemistry is in analytical chemistry, we understand error and we do everything we can to work within it, right? And so we know where we can ignore the errors, where we can use those errors, and what our confidence interval is in that errors. Really, analytical chemistry is mastering error, right? Organic chemistry is ignoring error. There is no such a thing as error. No. Okay, that's the big difference if you're ever curious. The graph should confirm linear response over the desired analytical range. Remember I was talking about that? It needs a linear proportional response within that range, okay? This is the assumption that's made using an internal standard. If you used an internal standard, you made this assumption, all right? And if this assumption is not true anymore, what happens? Will your internal standard do anything useful for you? No, you're going to misuse it terribly, right? And it will be garbage in, garbage out again. Notice the stress I always place on making assumptions, understanding the assumptions you made, okay? This is actually one of the #1 places I see people screw up, and it's just bad science. Honestly, it's probably something like 70% of the screw-ups in science or by medical professionals and all those are not understanding the assumptions they live by. So again, this is an example. This is that graph. It's pretty straightforward, right? Notice though, again, it's a linear response. It has to fit that linear line nicely. If it does not fit the linear line, then you would not have a slope, would you? And so the entire assumption of having an F factor would be silly.
So is the y-intercept being 0.0382, is that like kind of the...
I mean, I'd have to know the confidence interval for this data, but I would assume that that's within the confidence interval, the error limits of this data. And considering this is like 3 something, we're probably talking about whole numbers here, and then our first decimal place is our uncertainties. And so that would be well within the uncertainty. That'll be like 1/3 of the uncertainty probably. So, but yes, this is a uncertainty for that measurement, and it should be within smaller than the rest of our uncertainties, within the confidence interval we're working in. And again, like everything else, this is a trade-off, right? You can go through, use a Grubbs test to see if you can eliminate that point, okay? You could go through, figure out the exact uncertainty of this using our formulas we've talked about, the least squares. It's just least squares. And you could do more experiments, right? And get this narrowed down more, eliminating things with Grubbs tests as you need, right? So, you know, this is just an experiment like we've talked about every other time, right? This is not magic. And the stuff done by NMRs, that's just done by that usually the instrument manufacturer. And you can do a calibration, redo it. And yeah, it's not magic. It's not a black box. You know, no hand waving and, you know, poof. It's not what happens. It's all done by people. They can screw up. You can fix it. Okay?